Recently, I've decided to mess around with microcontrollers and to know how they work, what can we do with them, and essentially dive deeper inside microcontrollers. In this video series, we will dive more into AVR microcontrollers. These microcontrollers you can find on Arduino, most of them. For example, this one is Arduino Nano. On Arduino Nano, you can find microcontroller that is called ADMega328P. But if you have Arduino Uno, which is, I think, more popular than Arduino Nano, it will be essentially same microcontroller, but just bigger than this small square. And that microcontroller you can actually take out of the Arduino board and program that microcontroller separately from the Arduino board. And for starters, I just wanted to go through the Arduino itself. We have microcontroller, which is this one, on top of Arduino. And Arduino itself is a development board. So essentially it's a system of different components. And the heart of the Arduino is this microcontroller, ADMega328P. This microcontroller was developed by, I think, a company called Atmel. And this company right now is called Microchip. On the Arduino board, we also have this button, which is reset button. So when we press it, it will just restart our Arduino. We have crystal oscillator, which is this small silver thing, which just tells our Arduino what clock do we have, what time do we have. Also, what we have here are 4 LEDs and of course 4 resistors to drive these LEDs. One of them, which is called L, this LED we can program. This is special LED and it actually has its own name, LED built in. So when we want to, for example, blink this LED, which we will do in this video, we will reference to this LED as LED underscore built in. But again, this is all Arduino code. This is not actual C code or C++ code. This is Arduino code, which is, of course, different. And if we want to go beyond Arduino and just program microcontrollers bare metal or raw microcontrollers, we need to program them in C or other languages like Rust, which is getting popularity more today. But in this series, I will use C. So what else do we have is this IC, which is integrated circuit. And this integrated circuit is USB to serial converter. So what this means is it will translate the protocol of USB to serial so that our microcontroller, this one, can understand what we mean by the code or what these zeros and ones mean. And essentially, this protocol, what is this? I mean, any protocol in electronics, in programming, is just a way of communication between different computers, microcontrollers. And in this case, we are using USB because our computers, our laptops, they understand only USB. And unfortunately, this microcontroller, ADMega328P, does not understand the language of USB. So, in simple terms, they will not understand each other. And again, what this means to understand the USB language, USB protocol, is just to tell this microcontroller what these zeros and ones mean. And probably, as you know, microcontrollers and any computational machine, computer, microcontroller, they speak zeros and ones. But these zeros and ones we can interpret in many ways. So for example, these zeros and ones can be in pulses, but we don't know what each pulse means. For example, if it's going from low, from 0 to 5 volts, or from 0 volts to, let's say, 5 volts, or 3.3 volts, or even 12 volts. Some of the protocols use 12 volts. So we need to translate this and tell microcontroller that we will use, let's say, 5 volts as high pulse and 0 volts as low pulse. Or it will be logical 0 and logical 1. Also, what we want to tell our microcontroller how wide this pulse will be. So for example, we want to send 2 pulses of 1. So we will send, for example, 0, 1, 1, 0. And what we need is 0 volts, 5 volts, again 5 volts, That means we will stay on this level, and then 0 volts again. But this one pulse can be interpreted in different ways. So was it only one logical high? Was it 2 logical highs? 3? Maybe infinity? So that's why we need to translate these bits, bytes for our microcontroller. Okay, so now we can just go to my desktop and I will show you the initial code that we will use to blink this LED and how we can make it more like raw programming of this microcontroller. Okay, so this is the first thing that you will see when you open Arduino IDE. And again, I'll assume that you already know how to use it and you have already it installed. And also another thing, I'm using Arduino IDE 2.3.6, which is newer version, and it will look different than the older version. So what we want to do is to open the LED blinking example code. And it's actually already installed with Arduino IDE. So what we want to do is to press File, Examples, Basics, and Blink. It will open a new tab, and now we can see the LED blinking example, which is down there. I cannot scroll it. So that's why we need to delete all these comments. Here we go. This is the code. Again, this is an Arduino code, because in C we'll program it very differently, and we will not use all these functions that we will have here, digital write, delay, even delay, it is Arduino code, and even these things, function loop, setup. But for now, let's just go through them and let's see what we have. So first of all, we have a void setup. This is a function that will return nothing. And what we have here is another function, which is pin mode. Pin mode is a function that takes 2 arguments. We can see it here. These 2 arguments are uint8 pin and uint8 mode. So these 2 are 1 byte or 8 bits, unsigned. It just means we don't have sign, and integer. So this parameter called pin and the other parameter called mode. And here we can see that we set these parameters here, which is LED built-in, this is first parameter, and second parameter output, which is output again. Because we want to blink LED, we will set it to output so that it will supply 5 volts on this pin. And if we hover over this pin, we can see that it's a macro. And this macro, it just means that whenever we have this thing in our code, 13, this number 13, we will essentially substitute it with this LED built-in. So essentially what we can do is just, instead of this, write 13 based on the little documentation that we just saw. And by this, we just say that we will set pin 13 to be output. And if I'm not mistaken, according to this datasheet from Arduino, this is pinout of Arduino Nano, we can see here that this thing, LED built-in, that we just saw, is a pin 13 of Arduino, digital pin 13. And we can also see something called PB5, which is same here on the LED built-in, which is PB5. So this just means that this is same pin that we have here. Next we have a loop function, which will just do whatever we have inside it forever. What we have here is another function, digital write. And what this function does is it takes, again, 2 parameters, and it just says set whatever pin we have in the first parameter to whatever value we have. And this value can be either 0 or 1, or high and low. So we will set pin 13, or we call it LED built-in, to the value of high. Then we call again digital write, and in this case we set the LED built-in pin 13, to low, or 0. So it's done uploading, we have output, and it tells us that this sketch uses 924 bytes, not bits, of program storage memory, or memory where we can store our code. This is actually a lot for just blinking an LED. By the end of this video, we can shrink it down to, I think, 100 something bytes. And now we can start to shrinkify our code and make it more C. Okay, so the first thing of our optimization of the Arduino code, what I want to do is to write, instead of pin mode, this line here, which is ddrb equals 0b and this sequence of zeros and ones. This is a binary number. Essentially what it does is same thing as what pin mode does. So what is ddrb? ddrb itself is a data direction register B, or in simple terms, it's a block of memory that tells microcontroller in what direction data inside the register B, inside the block B, will go. So it's either input or output. In this case, 0 means input and 1 means output. So why did we write it here and not, for example, bit 0? Also, bit 0 starts here. So this will be 0, then 1, 2, 3, 4, 5, 6, 7. I think I did a mistake here. So it's not this. Yep. Like this. Like this. I think it should be like this. So 0, 1, 2, 3, 4. Yeah, this one fifth. We set the fifth bit inside register B to be 1 or to be output. How did I know that it is fifth bit inside register B, inside block of memory B? Or why not it's A? Why not C? Why not bit 1? So essentially, to know this, we need to go into the Arduino either datasheet, or in this case, we can just go to Arduino pinout. Same thing that we already saw. So if we take a look at the LED that we want to blink, it will be this LED, which is LED built in, or pin 13. This pin 13 has another name or another mapping, which is PB5. Also here, it is PB5. So this means that this pin corresponds to the port B5 or block in memory B, which is fifth bit. So we want to make first register B to be either input or output, or this particular pin D13 as Arduino calls it. We set it to output. And secondly, which we will do in a moment, we haven't done it yet, we need to set this pin D13 to be 1 or 0, because we blink LED. And again, that's what we do here in the setup function. So when we try to verify or upload this code, let's do verify first. Our sketch compiled, and the size of our sketch, of our code, gets down to 864 bytes. But here I want to make a side note. So when we did this, we essentially set all other bits, all other pins to be as input. And imagine that we have LEDs on this pin, which is PB0, and let's actually find which one is PB0. It will be this one. So if we hook up LED on pin D8 of Arduino, our LED will not work because we set that pin to be input. So that means it will not output any voltage on this pin. So this is not practical, and it's actually dangerous to write code like this, because we can just forget about this LED, or just imagine we have some sensor hooked up to this pin. So it will not work and we will have some problems with our system. So essentially we will not do this, but for now it's just easier to see which pin inside register B we will set as output. Okay, now as I said, we need to also tell microcontroller to output voltage. High voltage, either 5 or 3.3 volts, whatever your microcontroller is on that particular pin inside port B. So that's essentially what digital write function does. We write it as port B equals, and again, this is in binary, 0B. Then we tell it to set pin number 5, which is this one, 0, 1, 2, 3, 4, 5th bit, to set it to 1. Then delay for 1 second, and then we set it to 0. So here we have it. Then again, wait for 1 second and loop through it. This is essentially same what digital write tells us. But when we try to verify this code, it will tell us that the size of this program is 646 bytes. So now it uses 2% of program storage memory. Now that's much better. Also, it will run, I think, much faster. Now let's try to upload this sketch and let's see what we have on microcontroller. LED is blinking, same as before, every 1 second, and everything works. Now, where did I find this port B thing? This port B thing is something that AVR themselves, not Arduino, but AVR already wrote for us. So that means instead of this port B, what we technically should write is a pointer to memory address inside microcontroller. So this sounds a lot. This sounds very complicated, and if you don't know C and pointers in C, this will be a bit complicated, but essentially what it does is it creates kind of like a variable, which is pointer, that will point to memory location, like actual physical memory location block inside our microcontroller. This memory block they called port B. And when we will write C code, actual C code in the Arduino IDE first, we need to import a library that tells compiler what is port B. Because microcontroller, of course, doesn't know what is port B. It only knows zeros and ones, and these zeros and ones AVR wrote in their library, which is called avr/io.h. which is header file. Or what you can do also is to go to the ATmega 328p datasheet. Here you can find in the section 13.4 register description. It's page 72. So what we see here is register description. So essentially it just tells us what memory locations, what memory blocks are, and how we can use them. And here we can find DDR-B and port B. And as I said, DDR-B and port B are essentially names that AVR themselves thought about and came up with. But what we can see here is that this is a memory in the address of 0x24, or in hexadecimal 24. This just tells microcontroller where to find this memory block of DDR-B. It's something like an address, like actual physical address where you live, and it looks up 0x24 and it can find all the description about this port. And here we can see all the bits. This is an 8-bit architecture of microcontroller, so that's why we have 8 of these bits. Now port B lives inside this address 0x25. So that means we need to somehow write a pointer to this address and set its value of pin of bit 5 to 1 so that we can output 5 voltage. But again, as I said, AVR already did this for us, so you don't need to write any pointers to these locations. You can just reference it as port B. Okay, and the last thing that I wanted to show you is how we can write C code, like raw C code, and program microcontroller that is on the Arduino, which is ATmega 328p. So there is a lot of cryptic things like this. What the hell is this? What the hell is this? Well, let's just go through this one by one. First, what we did is we get rid of void setup function and void loop function. These functions are pure Arduino functions and we don't need them. Essentially what we do is we create int main function. So this int main function, it will return integer, and in particular it will return either 0 or 1, and depending on 0 or 1 our compiler knows. If it's 0, I think it's okay. If it's 1, it will throw this error in the console and say that we have an error, which is ID of 1. Next thing, we have to name this function as main, because almost every, if not every, microcontroller expects this function, or I would actually say every C program expects this function to be here, main function. This is just pure C thing that you have to follow. And inside brackets we have void. It just means that this function will not take any arguments. So first two lines actually, these are pure AVR libraries. And as you can see actually here, AVR, this is not Arduino. And what they did is they included, for example, this io.h. We could remove these libraries, but again, without them, we needed to write pointers to these registers. With this library, we can just use DDRB. And second, as you can see from the name, we just add delay. This delay in milliseconds. I set it to be 500 milliseconds or half a second, just to see the difference between first program, which is this one, and this one. Next, we create something called macro. This macro is just something that will replace this thing that our microcontroller doesn't understand, which is we have here. This is human readable thing. We can name it whatever we want. And this thing is port B5, pin 5 of port B. Sorry, not pin, but bit 5. Next, this thing. Instead of just writing DDRB equals 0B00100000 as this, we can write this. So this is essentially similar to something that I will write right now. So this thing and this thing, they are same, but written in shorter form. So this one. So what do we have here? Here we have this interesting thing, and essentially what this says is put 1 into this place. This place will be PB5 or port B5, which is here, bit number 5 of port B. So instead of setting individual bit like here as 0, 0 or 1, we will do this. Put 1 into this place and leave other bits as they are, whatever they are. Then what we do is we OR. This is I think called Boolean algebra. And essentially what we do is whatever value we have inside DDRB, let's say it's this value, 0, 0, let's say instead of 1 we have 0, 0, 0, all zeros. Let's just say for this conversation, they are all zeros. We say, take this value of all zeros and OR it with whatever value we have for this one, which will be 0, 0, 1, 0, 0, 0, 0, 0. And essentially it will look something like this. 2, 3, 4, 5, 6, 7, 8. So 8 zeros. This is DDRB. Then we want to OR it with this value. 1, 2, 3, 4, 5, 6, 7, 8. With this value here, which is this one. When we do this operation of Boolean algebra, what we will get is, in reality, we will start from the end, because this is first bit, this is second bit, and so on. But just for this conversation, it'll be easier to write me like this. So 0 or 0 will give us 0. Again, 0 or 0 will give us 0. 0 or 1 will give us 1, because that's how OR operation works. 0 or 0, again 0, and all zeros. So that means the new value of DDRB here will equal to this value. And that's essentially what this thing is. You can also think of it as something like this. Probably you've seen this. I plus equals 1 or I plus equals 10. I don't know. This just means I will be whatever current value of I is plus 10. These are similar things, and if you saw this thing, you know what this is. This is essentially same thing. And probably you would wonder, why not make it AND operation? So something like this. Let's just do this. 0 and 0 will be 0. 0 and 0, again 0. 0 and 1 will be 0. And all other are zeros. So as you can see, we did not change value, so it will be all zeros. That's what we don't want. Another operation that we have is NOT, that will just flip all the values, and of course we don't need that. And the other operation is XOR, which we actually have here. This operation will just toggle like a switch on off particular bit, and in this case this value. So again, let's just say port B is this value, which is all zeros. This thing, we say put 1 inside port B, bit number 5, which is this one, and we want to XOR it. XOR is another operation. So 0 XOR 0. XOR operation tells us that we can have 1 or other, but not both. So that means 0 XOR 0 will be 0. Again 0. 0 XOR 1 will be 1. 0 and all zeros. So now we can see what will happen if we upload this code. So let's just copy this one, and now let's upload, and I can see that my LED works. But before we see that, let's just take a look at the output. So we can see that our sketch uses 162 bytes of microcontroller memory, which is 0%. So we shrinked our program by essentially 9 times. And if we take a look at the LED, it blinks with 0.5 seconds. And just in case we don't see it, let's just try 100 milliseconds. It blinks faster. So yeah, it works. And this was part 1. And in part 2, I want to explore digital input. So how the input will work with button, and let's just say I want to press button, do something, press again, do something, and how this will work in pure C.